Hi everyone, my pleasure to be here. Thanks Uwe for giving such a good introduction and giving some interesting tools and features in order to understand this lecture. First, I'd like to know from the people in the audience, who is working on silicon here? It seems like, yeah, so, not so sure. So who is working on silicon, really? Okay. Who has knowledge on the silicon technology? Okay. Good. Nice challenge. So please ask questions during the talk. If I'm seeing that it's too tight in the schedule, I will at sometimes keep a bit the questions and we can have them during lunchtime as it was proposed. And anyway, you can reach me by email. You have my email in the slides if there is something. What? Yeah, I put them in white. I don't know why it's not, it's in blue now. Okay, anyway. This is interesting images, and I am pretty sure that you've seen them before. So this paper is the first PERC structure that was presented by Blaskers, and it was UNSW at the time in 1989. This one, maybe you should know this one much better. This is the Perl architecture, which was presented in 1994. So this one reaching 22.8% efficiency, this one 24, and this is the current architecture, which is 22.5%. And this is today. This is what we have in industry. So my first question is, what are the differences here? Let's say between, well, you can take this one and this one and this one. And the right answer is not 25 years. No volunteers?
If you look in the back side, you will find
for this one?
passivation.
Uh-huh.
Back side.
Yeah.
Passivation just passivated the lift.
Yeah.
And in third version, you passivated all the area.
So here, actually, now you have a point contact here also. So it's passivated here and it's passivated here. The point contacts are the same. Sorry, the thickness of the base? Yeah, it's one of the answers. But it's difficult to understand from this one, yeah? It's not to scale. Yes, you're right, exactly. So this is the Perl architecture. But here you also have a back surface field in this one. The doping, you mean, of the base?
Yeah, but I mean the area of doping. Like here we have a full area of doping.
Mm-hmm.
At the real contact, here we only have.
Here, you're right, but this figure is, we will see that now it's like this also. Okay, I will skip it a bit. So this is what was obtained. So this one, the PERC, so rear contact, and this one, a rear local contact, let's say. And this is what is a bit different. Basically, they were using FZ wafers, so Uwe will probably speak about the frozen wafers later on. So which are bulk material with really high lifetimes. There was thermal oxide around 1000 degrees. This is a base passivation, and even the anti-reflection coating on the front side is using silicon oxide. Contact opening was done by photolithography. I still recommend to read these papers, but this is the main interesting point here on what is the difference between yesterday and today. Metallization was done by evaporation, so on the rear side it was aluminum, on the front side 3 metals. On the front side they were using inverted pyramids. I think maybe Stefan will speak a bit about the inverted pyramids and versus the random pyramids. And you have also a diffusion-based selective phosphorus emitter here. Well, actually on this one. And now for the PERC industrial today, which is basically, we can say, a mix between the PERC and the Pearl. What you have, you need to have processes, high throughput, so you need to go now in the industry around 6,000 wafers per hour. So you can say that for lithography, it just doesn't work. It's not possible. You have to use standard material like CZ wafers. The thickness is much lower than this one. This one is around 300 microns. This one, so you have less than 100, you have at least 100 micron less, and it's going thinner. So Stefan will also speak about these challenges for the light trapping. And the lifetime is much lower. We are well below the milliseconds. The cost, we have to fabricate that at a cost which is below 30 cents per watt peak. And we have to be compatible with screen printing metallization, which is a standard for in the industry. So what I will talk about today, it's mostly this architecture. And I will explain you, and I will explain you as a technology how we came from ear to ear in the industry. But not only 25 years passed, actually the people in the silicon world, they worked. So basically they developed all these type of cells that I won't present today because it's a bit short and tight. But you have basically the P-type the P-type solar cells, the N-type solar cells, so related to the bulk material, so either if it's a P-type or N-type. N-type has much better lifetime. And you can say also that you have the world of the passivated, of the back contact cells, which are these ones here, all these ones here. And you will have the world of the passivated contacts that Uwe will speak about tomorrow morning. So I won't spend too much time. I won't spend time on this today. I will mainly speak how we went from this IPVF to the PERC, which is the mainstream in the industry, and all what we will discuss here will help you to understand what are the challenges to go toward these type of architectures in the future. And the future, it comes like in the next years. So first, probably if you're not working in the silicon world, you probably don't know what is a process flow for a fabrication of a silicon solar cell. So the mainstream technology in silicon has been for years what we name the aluminum BSF. So it means that you have an aluminum based contact on the rear side, creating a backscattering field. And this has been used and developed for more than 20 years in the industry, and now we're switching to the PERC. So all starts with the silicon wafers, which has been sold with now diamond wire saw. So you have a material which has damaged surfaces, so meaning that you have a surface which is mechanically grinded, and also you can have metallic impurities. So first thing that you do, you're doing a saw damage etch. So usually you're using KOH solution in order to etch some microns of the wafer. After that, you're doing some texturing, again based on KOH plus an additive. Initially it was with IPA, now it's other more industrial additives. And you end up here with random pyramids. Next, you're doing a phosphorus diffusion, and it ends up creating your PN junction, but as an effect, you have a PN junction all around the wafer. So obviously, you want to remove that. So the first thing that you're doing an edge isolation. So you're removing from the edges of your wafers the phosphorus doped layers. After that, you're depositing, usually by PCVD, well, almost only by PCVD, I guess now, the anti-reflection coating, which is silicon nitride. You can deposit your front paste, which is a silver paste, with firing through materials. So basically, under temperature, it will etch your silicon nitride. And on the rear side, you're depositing an aluminum-based paste, which will create underfiring, and the firing is firing of all the paste, create an alloy between the silicon and the aluminum on the rear side and creating a BSF. So this is the process flow, and this is where we are today. Efficiency around 20% for this kind of devices. The yield in the fabrication, so we are converting more than from the initial wafer, more of 95% of this wafer are converted into a 20% efficient solar cell. The throughput is well above 3,600 wafers per hour. This is quite a simple and lean process. If you count the processing steps here, you will count something like 8. Actually, in between, you add cleanings also. So it's not, when you see that actually in between, you always have cleanings almost. And the cost at the moment, it's around 20 cents per watt peak. The issue for that is when you look at the recombination current, so for these cells, you can see that at the VMPP, the BSF part here is a really high contribution. So it means that first, the BSF it's the layer that we'll have here at the rear sides as a main, is dominating the recombination losses. And so we have to improve that. Also, this layer has a poor performance in the near infrared. So I already mentioned the recombination layer. It's not bifacial, and as of today, bifacial cell it's something important in the PV world. You have quite a high consumption of aluminum paste, even if aluminum is cheap. It's always important to have cheaper cells, and there is a quite important degradation rate. So now that we have this understanding how aluminum BSF is fabricated, what are the main losses, so the BSF mostly here, we'll see what we can do in order to improve that and what the people did during these 25 years in order to improve from aluminum BSF to PERC. Clear for everyone? Okay. So this will be the main outline of the talk. So from ILBSF to PERC, 25 years of PV history. So this is the structure of your ILBSF. So the pyramid, the nitride on top, the P diffusion. At the rear side, the ILBSF. Here you can see it. You can see the aluminum, which is like some spheres. And at the interface, you will have aluminum silicon eutectic and also a P-type layer. And when you will go to standard monofacial PERC, you will have same, but on the rear side, it seems that you have something a bit different, which is local contact and passivation layers, right? So we will speak about rear surface passivation, parasitic emitter edgeback, contact opening, rear metallization, front optimization, and bug quality improvement. And everything relating to the limits, and that will be covered also probably by Uwe tomorrow. So let's start with what is the core of the PERC technology, the rear contact passivation. So UNSW papers, the two I mentioned, were using thick thermal oxide for the passivation of the layers. So thick, it means around 100 nanometers. So it's good, it's providing a really good passivation, but one of the issues is that at the time when it was developed, also the PV world was using mostly microcrystalline silicon wafers, which are really sensitive to high temperature processes, especially the really high temperature processes. And so going to 1,000 degrees in order to create a thermal oxide, it wasn't possible. So you have to find another way in the industry in order to do that. So first, the people say, okay, let's use the silicon nitride. It's already used on the front side, so let's try to put that on the rear side. Looking at what we name surface recombination velocity, so the lowest, the better. So it means the velocity at which an electron hole pairs will recombine. So obviously, the lowest the speed it is, the higher the lifetime, and so the higher theoretically you can get as a theoretical efficiency. So SRV was quite low, but they observed a reduced short circuit current values, and they said that basically it was due to the fact that that you will have a bit of positive fixed charge in your silicon oxide or your silicon nitride here, and which creating what we name a floating junction. So basically we will, through this quantity, these fixed charges, we will invert the type of the silicon. So the silicon here, usually it's p-type, and here you can see locally it could behave like an n-type silicon. And so you can see that you will have parasitic junctions, which is not good for the performance of your cell. So they said, okay, silicon nitride is not good enough. We can't use silicon nitride as it is because it has a lot of positive fixed charges. So what do you need? You need low DIT. So DIT is the interface density, interface defect density. So you want obviously to have as few as it is possible, almost none of them. So for example, this is the dangling bonds that you can have at the end of your crystalline silicon wafer. And you would like to have no fixed charges or negative fixed charges in order to not create a floating junction. So people first said, okay, but I really like the silicon nitride. So how can I do that? And I've seen that using silicon oxide, it's good, it works. So let's try to reduce the silicon oxide thickness and to maybe also deposit it in another way. And they really could do it. They reach really good SRV, again, with 10 nanometers of silicon oxide, and deposited in a lot of different ways. PECVD, also thermal oxide, and or other type of CVD-like processes. But well, not really, but some industrials are implementing that in industry. It still exists. For example, Centrotherm has that in their tools. But in the end, we will see that this is not the mainstream process. Also, I think that you maybe all know the heterojunction cells, so silicon plus amorphous silicon. So amorphous silicon is really well known in order to really well passivate silicon surfaces. So they said, okay, let's try this. So let's put amorphous silicon at the rear side of our cells. It works perfectly, but the issue is that amorphous silicon is not stable over 300 degrees somehow. You can improve that a bit, but not that much. So it's not compatible with firing processes like it's mandatory for silicon. So the thing is, now that we have what we said here, we want to have low DIT, no or negative fixed charges. We have this type of plot. So with the quantity of fixed charges, here you have the positive ones, here you have the negative ones, and here you have the DIT. You want to have lowest DIT, you can see that amorphous silicon is one of the best, and SiO2 is one of the best. Don't just too much it's from this paper, so basically they are really advertising their results. And after that, you want to have either no fixed charges or negative fixed charges. So in the end, you can see that aluminum oxide is one of the best candidates. So this is what the guys in the 90s tried to do. We are, in silicon science, we are always coming back to what was done in the 90s. I really recommend to you to also dig a bit into the archives, do a bit of archaeology in your literature, because it's always interesting. So the first demonstration of Alox dielectric layer in the solar cell was done in the 90s. Well, not just before the 90s, and they got SRV quite high, around 200, 300 centimeters per second. It was implemented in the new type of solar cells around 2 decades later by Agostinelli. They've shown that Alox can be deposited by a lot of different techniques. So PCVD, ALD, which can be standard reactors like batch reactor or spatial ALD by ICP, inductively coupled plasma, APCVD, atmospheric pressure plasma, or reactive sputtering. For all of them, we observed really good lifetimes and efficiencies. Something which is interesting to look at, it's this graph here. You can see that, are you comfortable with the injection density of the carriers in a solar cell? Kind of? Not that much, it seems. Okay, so your solar cell might work at different injection densities depending on the illumination spectrum and obviously of your cell architecture, right? What we can see that a solar cell, a silicon solar cell passivated here by ALOX, amorphous silicon or silicon nitride won't have the same passivation surface recombination velocity at different injection density, and you can see that for ALOX, it's much more stable, actually. So this is this slide is saying that basically this figure is saying that basically an ALOX passivated PERC will behave better all over the day at different illuminations than one which would be passivated with silicon nitride. And we've seen that silicon nitride is not the best material, right? After that, we can see here different type of aluminum oxide, and we can see that ALD aluminum oxide are the ones that are providing the best lifetime compared to reactive sputtering, and PCVD is not that far away. Nonetheless, something which is important to note is that ALOX is a really thin layer that we integrating in our solar cells. We will integrate between 5-6 nanometers to 10-12 nanometers only. And so we need to put a capping layer on top. And this capping layer has to, will improve the passivation using hydrogen. So the nitride, the silicon nitride, has a lot of hydrogen which are able to move towards your interface, and this is what you can see in this slide. So just an ALOX layer will have lower effective lifetime compared to an ALOX plus a silicon nitride stack, depending on the thickness. And please remember, we will be in this range. We will be below 20 nanometers. It's also protecting the ALOX against high temperature firing, because the ALOX, which is an amorphous material, won't like that much really high temperature of firing, which is around 800 degrees. Even if it's some seconds, it can be too much. It might damage the ALOX. And also something really important, it's to protect the ALOX from aluminum paste. And here I will count just a little story that we had when we fabricated the first PERC at IPVF. Maybe it's not a good advertisement if it's recorded. But we can cut. Okay, just between us. So the first time we fabricated that, we fabricated PERC, and we get performances which were basically lower than ILBSF. So like, how is that possible? And in the end, we worked a lot on the capping layers, and we discovered that our capping layer was not dense enough, and so we had our metallic contact going through our nitride. How did we see that? We fabricated our solar cell, we deposited the aluminum oxide, silicon nitride. We didn't open the area to take the contact, we fired through directly, and we could measure a solar cell, an IV curve. So without providing any way to contact the metals to the silicon, we could measure a solar cell. So keep that in mind, it can be helpful for you maybe. And it happens. And something which is important is that this hydrogen, there is a lot of hydrogen in this stack, ALOX plus silicon nitride, and you have to be careful of what you name blistering, so it will be like blisters that will appear at your surface, and that can be completely detrimental to the performance of your device. Only thing is, it seems that there is good blisters and there is bad blisters, and they are really difficult to identify. So maybe just now let's go. It's really the core of the APERC. This is why it was important to take a lot of time. Let's go now to the emitter edgeback process. So as we said, first, we are doing a diffusion and it goes all over the wafers. And you have, in the end, to edge back, you have to remove this phosphorus dop layer on the rear side. For LBSF, you didn't need that because you will create an alloy on all the surface, so it will directly hit your silicon. But for the PERC, it doesn't work. So if you want to avoid parasitic junctions, you need to do that. And so it was done. The main way to do it was using an inline etch-back processing, using wet processing with HF HNO3 plus an additive. It can be H2 SO4 or other type of processes or additive. And so basically, here you will have the wafer just standing and on top of the liquid. And so what comes handful also here is that it will etch this part here and also on the edges, and this way you don't need to do your edge isolation that we were doing before. One of the results is that you can go high throughput. You need to have a big enough tool, basically. Not that complicated. It's single side removal. You're etching some microns of the silicon. The question is, depending on how you're playing with the additives and with the concentration of HF to HNO3, again, there is papers from the 70s on this, you can go from isotropic to anisotropic etching. And so the question here is, do you want to go isotropic? Do you want to round the pyramids? Or do you want to flatten the surface? What is the best for light trapping? And so, again, maybe Stefan will speak a bit about that. But so this is a paper from IMEC. And so this is a surface texture. So you can see the pyramids in the rounds of some microns. And after etching, so the pyramids are always like this with an angle of 54 degrees, something like this. And after etching, they will basically flatten a bit. And what they observed is that there is somehow a maximum for the JC, so you're increasing them a bit by etching the rear side. Also, it comes handy because it's more difficult to passivate pyramids with a really sharp angle. So VOC can be also a bit improved when you're etching. So this is why overall the efficiency is a bit higher when you're etching something like 4 to 6 microns. But, sorry, there is still the last part is that we have lost absorption because we are reducing the thickness of the silicon. It's already a poor absorber, so if you're reducing the thickness, you can also reduce a bit the current in the end. Okay, so now the other really important stuff is how do we open the contact here? Because we have to take the contact out. Otherwise, we just do absorption, separation of the carriers, and if there is no collection, there is no efficiency. So everything was made possible thanks to the introduction of laser. And really high throughput lasers. So basically, they're using lasers. It's usually nanoseconds or picoseconds lasers. Usually green. UV can be used, but in industry at the moment, they still don't like that much UV because the lenses for UV, the optics, it's much more sensitive to dust, and so less reliable. And so here you have your inline laser, and you have a scanner head. So it's basically a mirror which will deflect the laser beam at a really, really high speed. Basically, you can open a wafer, the rear of your PERC here, in something like 1 second. It's really, really fast. The question is, so yes, you want to have nanoseconds or picoseconds in order to avoid damaging of the silicon wafer. UV or green, it's better because you have better selectivity between the layer and the silicon, and it's high throughput, obviously. You can do line dash or points opening. So basically, either you're opening on the full width of your wafer, you will do like this, or you will just make a point. We will see that it's important because obviously one of the main losses is still the J0 metallization that we will get here. So the recombination current at the where we open the wafer and where you have contact between the aluminum and the silicon. But you will see now that this is a main issue, and it has a really strong impact on the local BSF formation. So let's talk about this. So how now we modified this metallization from the full part only to the local contact, and what was the modification? What did it impact? Okay. So here it's an ILBSF. Here you have a PERC, so full surface metallization, local metallization. And this is what you have usually. You have around 30 microns of aluminum, roughly, I would say, using screen printing. And here when you have a local BSF, what you have in the end, you have local BSF, so P-type silicon, which has a P+ type silicon, which has been created by aluminum doping within the silicon. So it's really, I don't see if you're seeing that right here, but it's a silicon, it's a really small layer within the silicon, usually by SEM. You can see it's due to the different contrasts that you can see. It's usually a bit lighter. After that, here, within this opening, you will have the eutectic between the aluminum and the silicon. So if you're looking at the aluminum silicon phase diagram, you will see this. And here, after that, you have the aluminum. But when you fabricate that, and we did that also at the lab, obviously, when you do an electroluminescence imaging, and sometimes you're just measuring your cell and you're seeing that you have a high series resistance, you see that, and you do SEM in order to understand what happened, you can see that you have some voids. So somehow here, it seems that your silicon went in, or your silicon went out and aluminum went in, but at some time the eutectic is not here. And in some of the places you have that, and you say, okay, what happened, and how can I manage in order not to have this, because this is a main issue for a PERC. It will result in poor fill factor, in poor series resistances. So everything can be controlled somehow through the diameter, the contact opening diameter, the pitch, because and the aluminum available volume, let's say, and the firing temperature and cooling. So the main rules are this one. Smaller pitches, so here, same quantity, same paste, same quantity of aluminum. The only thing that is changed, it's small pitch, big pitch between the laser openings. Smaller pitches seems to be preferred, because actually there is a competition of fluxes so basically your silicon is drained out from the wafer and you have aluminum going there. But they don't go at the same velocity. So because if I remember correctly, and I put that here, I don't remember which one is going faster, to be honest. But if you don't do it carefully, so if you're not cooling fast enough, you will have some voids. And other thing that has been that have been put in place in order to improve that and to tackle that issue was to use aluminum paste with a bit of silicon within. So basically 1%, 2-3%, because this way, in order to create this contact here, it would take out a bit of silicon from the wafer, but not only. There is already silicon embedded in the paste. And it allows to have a better control of the process. There was some other metallization which didn't make it to the industry. For example, some people said, okay, yeah, but if you have to do this laser opening, then screen printing, then firing, and it's difficult to control. Maybe we can do something a bit leaner, which is we deposit directly the metal, and we're firing through a laser, using a laser through the contacts. So basically they were doing evaporation, sputtering of screen printing of aluminum on the full size of the wafer, which is fully passivated, and after that just firing a laser on top. And it creates something like this. It melts the metal and it goes within the silicon. The results are quite good, but in the end it doesn't create a local BSF as deep compared to the standard way when you do LCO plus metallization. So LCO stands for laser contact opening. Some people also at Fraunhofer ISE, they did some foil metallization. The name of the process is foilmet. And they fabricate, so basically they have something like 8 microns aluminum foil that they're putting on top of the silicon wafer. So there is an air gap in between. Stefan will explain you why it's good to have an air gap. And they are shooting a laser on top of the aluminum, and you're creating a welding here at the surface. It seems that the results are as good, and it seems that it's a bit better maybe for the near-infrared properties because of this air gap here. Still, it didn't make it to the industry.
Can I interrupt you? I never realized, can you come back to the previous slide? That actually the aluminum is quite porous.
Yeah, it's really porous.
Yes, and so probably the optical properties of this aluminum are really bad. So
Yeah, no, it's not as good, but it's not that much important because you also have alox and silicon nitride between the silicon and the aluminum. So a lot of the light is already reflected before. You can, if you look at EQEs between ILBSF and PERC, and after that heterojunction, you will see that definitely between ILBSF and PERC there is a huge change in the EQE in the near infrared. But heterojunction, obviously, it's better, but not as much. But obviously, yes, screen printing contacts are not good mirrors, and you have parasitic absorption of the metals. Let's go for front optimization. I still have a bit more than 5 minutes, so it should be okay. So we said, okay, now we improved the rear side. Let's try to improve the front side. What can we do? So the main issue with the front side is, let's say, the Auger combination that we can have here. You need to have allow enough sheet resistance in order to have a proper contact with the metal here. So in order to do that, basically you have to dope, and you need to have a doping level at the surface in the range of 10 to the 19th cubic centimeter. It's a depth of doping around 300 nanometers. Below the contacts, you have recombination losses, which are currents, which are quite important, around 1,000 femtoamps per square centimeters. So you want to reduce that. So first, you want to reduce that, and you want to avoid having a lot of Auger recombination on the full area of your wafer, because it's a huge area, right? It's around 244 square centimeters. So the first thing that you want to go, you want to go for lower doping, so higher sheet resistances. But you need to have proper ohmic contact, otherwise it's nonsense to do that. So the guys, they try to implement what we name selective emitters, so to do only high doping just beneath the contacts. And the way to do that is to fire a laser. The best way to do it is to fire a laser through the phosphorus deposited oxide, which helps you to do the phosphorus doping. And you created this cavity, which is much more p-type doped, and you can end up with having this type of doping obtained by ECV. And this way you will reduce the J0 of the front side, let's say, and emitters. So this one is Yes, it's only on the emitter by at least dividing by 2. This is now a standard process in industry using a nanosecond lasers. Something interesting, it's also, in order to do that, you need to improve the bulk. Bulk quality at the beginning was coming from the microelectronics, let's say, and they had really poor bulk quality because in microelectronics they don't need to have such good quality. They need to have a really good surface. They are creating cavities, doped in order to have electronical transports. But for the for silicon solar cells, what we need the volume and quality in the volume of the bulk. So we needed really development in the bulk quality by itself. So in the 70s, again, in silicon, we are always come back to the old time. They discovered the first thing that we name, that was named later on the LIDs, so the light-induced degradation, which was that after, not only perovskites could see degradation after light illumination, silicon also have seen that. And so after illumination, they were seeing a JST loss. But the strange stuff is you can recover it with an annealing at 200 degrees in the dark. And so later on it was named, this is what we name light-induced degradation. Beginning of this last decade, let's say, they studied that intensively, and they discovered that this was mainly due to the boron-oxygen pairs that are created in your wafer. And so there is mitigation losses. First, if you have lower doping, you have lower LID. So this is what you can see here. So the lower the doping, the higher the resistance, and so the lower the LID. And also by, for example, replacing boron by gallium, you don't have this effect. Still, at the moment in the industry, there is not really, I think, a lot of silicon suppliers providing gallium-based wafers. And you don't need to have all of you don't have to remove all the boron. If you're reducing the quantity of boron, it helps a lot. You can maybe replace 1/3 of it. I don't know the quantity, it's just trying to explain. Also, the PERC are more sensitive to the IPVSF because they have much better light trapping, so they will create much more electron holes pairs at the rear side of the cell, so they have to travel completely through the wafers. So they showed that the BOF defect can be permanently deactivated, and mostly this can be done using illuminating and annealing at 200 degrees the cells at the same time, and it can be done using LEDs or laser, and you have to control the cooling. So basically, usually it's done in the firing furnace. After firing the contact, there is an add-on that you can have. This is my belt. So I'm firing the contact, and here I have a small equipment where I will illuminate and heat at 200 degrees, and in order to deactivate this lead effect. The cooling is crucial. Here you can see the effective lifetime gain you can have during this process with a belt at 7 meters per minute and one with 1 meter per minute, and the effect is quite shocking. But like always, when we discover something and we heal it, there is a new effect appearing, and this new effect is LETID. So this is a light-enhanced temperature-induced degradation. And it seems that it appears, it's basically the same thing, but it appears when your cells work at higher temperature. And you say, when you're in the lab, you say, yeah, I'm flash testing at 25 degrees, so no issues. But in real life, your cells in a PV module, they are at 50, 60 degrees and higher sometimes. So this is something that we observe in real life condition. So some suppliers say that they elite. It's something like 1 to 3% degradation that has to be expected. Some studies tend to incriminate the passivation layers, and especially the hydrogen, which is contained in the passivation layers, especially the silicon nitride, probably also the aluminum oxide, and my question for the silicon community is what will happen with the polysilicon contact that we will have, or the amorphous silicon-based heterojunction cells, and is this something that could happen if we were doing that on P-type? Some mitigation routes. The first one is gathering. So this is when you're doing the emitter, high temperature. I think I'm almost over time, so I should stop really soon. This is done to create your emitter at the front side. If you're fabricating a fully passivated contact cell, you don't have this step. So what will happen in the future if you want to do a passivated contact cell with a P-type wafer? You can replace boron by gallium, or partially. You can reduce the wafer of the thickness. You will have less boron in the end available. So this is what you can see in this slide here, in this figure here. You have to control, you can also control probably the hydrogen. And something which is not thought too much about when maybe in this community is that there is a work to be done at the module level. Because if you can make that your module won't reach 70 degrees and will always work below 50 degrees, you won't have this effect. So if you can work in order to have a near radiation of the infrared, it will help in order to mitigate the effect of LETID. And finally, and just to introduce what you will see tomorrow, is that this is a PERC line. So now I will let you look at it, and this is the process flow that we've been through today, basically. So you have it in the slides. Here, it's this is basically where we are in industry at the moment, even if it's stopping in 2016. But in industry, we're now fabricating cells around 22.5% efficiency. And when you're looking at the analysis of the losses, you can see that in the end, the rear aluminum contact is still quite a high important loss. So it means that how can we tackle that in order to improve again the cells? So you can improve the emitter structures. So it's implementing this selective emitter, which we discussed that it's already being done. Improve the BSF structure, so going between dash to local points, and maybe use boron-based pastes. Improve the material quality, not have any boron oxygen pairs. We also have been working on that. Advanced metallization technologies. We can say this is also something which is being implemented today. Now the cells are 6 bus bars, 5 to 6 bus bars. Some of them are bus barless. So this is interconnection that has to be done at the module level. Advanced surface passivation, allox nitride. So basically, everything has almost been implemented. Indeed, we already achieved, so this is long G, 24% efficiency for a PERC. So probably doing all the tricks I explained before. At the moment, it's not cost efficient, but it has already been done. So the question is what comes next, and you have to go for the PERC. You see that the next step is the passivating contact, and after that, probably the IBC, passivated IBC, let's say. And so for the passivated contacts, obviously this also come back to this one here, that we will improve the loss here at the rear contact. And so we have to reduce the J0 metallization, and you can do that, which will improve the VOC of the cell and go above 700 millivolts. And this can be done only with passivated or passivating contacts. And I just split into two things. You have the passivating contacts that I will speak mostly with the polysilicon approach. The main challenge is it has to be compatible with screen printing, especially for the P-type layer. We're using aluminum-based paste, and they are spiking into the silicon, so you want to avoid these kind of things. If you want to have passivating contacts on both sides of the wafer, you have to avoid the UV parasitic absorption. You need, maybe it's a question, to demonstrate potential implementation on P-type compared to N-type. If it's on P-type, you have to see how what will be the impact on of the LETID. And to show that maybe you have a better bifaciality than what you can have with PERC, which will be limited around 80%. Heterojunction is a type of passivating contact. Again, I think Uwe will discuss a lot about this topic tomorrow. I think the challenges for heterojunction is a bit different because it's already now in mass production at REC in Singapore, and it's to demonstrate that LCOE, you can have a LCOE, so levelized cost of electricity, cost advantage, even considering that this is a high capex technology. Especially compared to polysilicon passivating contact approach, which can be done improving and enhancing a standard PERC line. For the heterojunction, improve the JSC because there is a parasitic absorption of the amorphous silicon on the front contact, and this is why a lot of this community is working a lot on metal oxides, passivated contacts, and demonstrate stable process in the fab around 6,000 wafers per hour, and this is a challenge with such thin layers which have to be homogeneous. So basically it will be like passivated contacts, PERC like, or heterojunction like polysilicon or amorphous silicon like, and after that the question it will, all of them are saying we are going to go IBC, but will that be with amorphous silicon, so heterojunction based IBC, or polysilicon based IBC, and which will enable to get up to almost 27% cell efficiency, meaning 24, 25 module efficiency. And with this, I'm ending the talk, and happy to take any question. And I'm slightly late.
Do you have some very quick questions?
Or otherwise, there will be. We can have lunch together for the ones who want to have questions also. But you.